Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today I'm going to do something a little bit different. We're going to have a rebroadcast of an older video that covers aerodynamics, stability, and especially dynamic stability of flying wings. It's been a very popular video, has thousands and thousands of views, which for my channel is a lot. And I thought, given that there's so many new subscribers, they probably missed that one. It's buried down about 3 years ago, and they might enjoy it. It's kind of long. It's about an hour and 20 minutes. It's like a full-length movie, but people watch it in chunks, and some people have watched it 4, 5, 6 times. I find that hard to believe, but they've done that. Anyway, I thought it'd be good to rerun that. People seem to enjoy it, and it also gives me a chance to do a little update on it. I'm getting ready to shoot more videos here in the shop about results from recent flight tests that we had at El Mirage. And I thought it was a good time to convey to everybody some of the lessons that have been learned in the recent flight tests. One of the main things that I seem to have come across is that the auto yaw system on full scale doesn't seem to operate as effectively as it does on the models. So I would caution everybody that anything that I say about the auto yaw system in the upcoming video, just ignore that. You can completely forget it. Right now, I'm flying the wing with the winglets fixed closed, as if they weren't movable at all. And I suspect as we move along here, I'm going to be putting in rudder pedal type controls so that you can have both yaw control during flight and speed brakes, dive brakes for final approach to get into tight fields. So the flaps combined with being able to deflect both winglets outboard like this will mean that the glider can come in and land in a really tight space. So that said, I welcome everybody who hasn't seen this video before to watch it. I hope you find something useful in it. At the very least, you're entertained. I cover some topics that are not covered very often. And if you do like it, I invite you to look down below here, look at the heart-shaped thing that says thanks, click on the thanks button and send me your thanks. And that'll be greatly appreciated. Any amount helps. Gas is outrageously expensive to go out and test fly. It takes about $300–400 just to go out and do test flying for a day, just because of the miles that I have to drive. So any donations are very welcome. All money goes directly to supporting the test flights of the glider. So that said, please enjoy the video, and here we go. Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today's video is going to be, well, lengthy. So you might want to hit the pause button, go get yourself a nice beverage and snack, settle in, and we're going to talk about flying wing aerodynamics and some of the recent trait studies I've been doing for my final design. So what you're looking at here on the screen is the original Klingberg wing cycling through a range of angles of attack, and behind the wing you see yellow lines that represent the induced drag that's a result of the lift being produced by the wing. What you see here in the simulation is very close to what I actually built and flew. It was a reasonably nice flying aircraft, so I'm going to use this as a baseline for my new design efforts. Now, the program that you see it running in is called XFoil 5. Like all numerical analysis programs, it is based on aerodynamic theory. The numbers that it produces are not necessarily correct in an absolute sense. In other words, you can't look at a number and say, yes, it's exactly that number. But these programs are excellent for comparing various configurations. So consequently, they're very good for doing trade studies. That said, I'm going to be using this program to establish the final washout pattern for my Klingberg Wing Mark II. So you can do a variety of things with this program. It is based on a combination of panel method and lifting line theory, and you can do basic aerodynamic studies. You can do performance, static stability, and some dynamic stability. Overall, it's a very useful program. It's been worked on for a number of years. It's been around since the early 80s. The basic form of this program, very early version of it, is what was used to analyze my original Klingberg wing and set that design. So the original Klingberg wing did not have any winglets, so it was designed to have reasonable performance and good stability without winglets. There was an option to put winglets on it. I never got to that point. The wing flew reasonably well without winglets. Its one drawback that it had is that as you entered, if you were flying slow and you entered a turn, you would get a significant amount of adverse yaw. And this is typical when you use elevons for control and you don't have winglets. On a pure flying wing without winglets, adverse yaw is really kind of a moot point. Just doesn't make any difference. One wing's further forward, the other wing's further back, or vice versa. The wing doesn't know the difference. The wing doesn't know where the nose is pointed. The wing that's further forward is performing better. The one that's further back has less performance. But net, it's the same. Its basic issue is that it disturbs pilots, especially pilots who have a lot of experience that have been taught that adverse yaw is bad and causes a lot of drag. Well, on a pure flying wing, that's just not true. The drag is the same no matter what the yaw is for reasonable yaw situations. So pilots would fly the wing, both the model and the full size, and they'd see that adverse yaw and they'd have no way to correct it, and it would just bother them. I taught people how to fly model airplanes on my flying wing, and people who didn't know the difference, it didn't really bother them as much. I would tell them to just simply ignore the adverse yaw and pay attention to where the aircraft is flying, not where the nose is pointed. In other words, I taught them to pay attention to the velocity vector, the direction that the aircraft is actually moving or headed towards, rather than where the nose is pointed. I often joked with people that if I just rounded off the nose, nobody'd know where the nose is, and then it wouldn't bother anybody. But few people saw the humor in that. The little trick with the original wing was to just press the nose down a little bit, pick up some speed, and then roll into a turn, and there'd be almost no adverse yaw. Okay, so it was okay, but it bothered some people. So for my new design, I'm going to have winglets. We're going to completely kill all of the adverse yaw. Plus, the winglets allow me to adjust the design of the wing to improve the L over D over a wider range of angles of attack and thereby improve the general performance of the wing. And what we're going to look at here in the aerodynamic studies is whether or not you can gain that performance without giving it all back due to drag from the winglets. So it's an interesting task. These are trade studies that I've worked on for years and years and years, and I believe I've arrived at a solution that is actually superior to the original design. Okay, so that said, we're going to go look at some of the other modes of this program. I'm actually going to stop the animation here. I'm going to come over here, get my cursor there, turn off the animation. I'm going to run the angle of attack up to somewhere near its maximum, 14 degrees there. And we're going to look at the span-wise lift distribution. Let me get on the right graph here. So there is the span-wise lift distribution for this wing. And if you've studied flying wings at all, you'll know that this is pretty much a classic bell-shaped lift distribution. And flying wings often have this lift distribution because it provides reasonable yaw stability and yaw damping and reasonable performance. In other words, it's a compromise between the two. The more you get towards an elliptical lift distribution, as if this lift would come out here like this and then arc down out here, you're going to have higher performance, but much less yaw stability and yaw damping. That's because the forces are actually summarized at a point that's further outboard along the wing. In other words, the mean aerodynamic chord and the aerodynamic center of the semispan is further outboard. So any disturbances of the wing act upon that point. Therefore, if there's a forcing function for yaw, it has a much greater moment arm with an elliptical lift distribution than it does with bell-shaped, and therefore the wing tends to be less dynamically stable and yaw. It wanders around. As you pull the aerodynamic center in towards the middle of the wing, that moment arm gets much shorter, and disturbances are not as great, and you don't have problems with yaw damping or Dutch roll or other stability problems. Now, the other thing that is often done with flying wings, and I'm going to run this down to a lower angle of attack, down here 4 degrees, you'll see out at the ends that the lift distribution actually goes flat. Some flying wings have this arc back up. And what that is that's due to the washout of the wing and the airfoil selection. So at low angles of attack, this wing actually demonstrates a small amount of proverse yaw. Al Bowers has an excellent description in one of his papers, and in the video here you'll see a link where you can go get that paper, and he explains and diagrams why this particular lift distribution will give you proverse yaw. And that's why putting the nose down just before entering a turn would actually eliminate the adverse yaw in this design and give it better performance. You're actually changing the lift distribution across the wing and creating a situation where you're going to cancel out most of the adverse yaw. So the advantage in this particular aircraft is no drag from winglets, but you do have to pilot it in a special way. You have to just kind of ignore where the nose is pointed, and when you enter a turn, you got to dip the nose down a little bit if you don't want that adverse yaw. And there were a couple of other idiosyncrasies of this design that made it less than pilot friendly. Okay, so now let's go over and look at a performance curve. Let me get on graph 4 here. I'm going to show you L over D. This is coefficient of lift over coefficient of drag, which of course is the same as saying lift over drag, or the basic performance of the wing. This versus the angle of attack, we're going from about, let's see, what does it say, about 4 degrees here. We run up to 15 degrees angle of attack. And the peak performance here is at about 6.5 degrees angle of attack. Now, you're going to see the Y value here is at 28.32. And let me tell you, the wing never, ever achieved, nor was it designed to achieve an L over D this high. And that's what I'm talking about in this program. All programs like this are going to give numbers that are invalid. Most likely they're numbers that are too high. The actual value for L over D for this wing was somewhere around 20, 21, maybe 22 at best. So the actual performance of the wing is way down here. But we're going to do this on a comparative basis, and that's where the program really shines and helps me make decisions on how to change the design to achieve a good balance between handling and performance and just basic stability. Now, if you don't look at other curves, you'll say, oh, that's not a bad curve. You know, it got pretty good L over D. But actually, the L over D range here compared to conventional aircraft configuration is relatively narrow. The range over which you have good L over D only spans a couple of degrees angle of attack. And what that means is, as you slow the aircraft up or speed it up, you lose performance rapidly. And that was definitely borne out in this design, both in the model and the full-size configurations. As you slowed the aircraft up, it was not a floater. It would not just hang there on the lift and float along, and nor would it speed up and go really fast. You could put the nose down and pick up some speed, but you'd see the performance really drop off. So basically, it was a one design point aircraft. It had a trim condition where it had really nice performance, and you could have small variation on either side and still do well. And that was just how the design was, but it was stable and flew well. So what we're going to attempt to do here is broaden up this L over D curve so that we have better performance over a wider range of angles of attack. I wanted to take a moment here to reference a gentleman who's done a lot of work on flying wings. That'd be Alon Crew from Stanford. He was one of the key designers of the Swift foot-launch sailplane, which is proved out to be very successful. I believe he was also involved in the design of the Millennium. He's worked, done a lot of work over the years, a lot of analysis on flying wings. He's fascinated by them, and he's done great work. And I thought it'd be interesting to reference a point that he makes in one of his papers about flying wings. He says here, right up here, one difficulty with this is that it is very easy to design a very bad tailless aircraft, while conventional design wisdom leads to quite good conventional design. And that point is very well taken. You can build flying wings, design flying wings, and build them that actually handle well, have good stability, are a pleasure to fly, and they just really have stinky performance. They have bad L over D. They get a lot of drag due to a variety of factors that have been diddled with to get them to be stable. It's a trade-off with flying wings. You have to trade off a little bit of performance to gain nice handling characteristics. Now, Alon, in this paper here, which I'll put up a link to, you can find the paper, read it for yourself. He goes into discussion about how to balance those factors out appropriately such that you get an optimized tailless design. And it's a quite interesting paper. I use some of his work from this paper to do my current Mark II design in terms of planning out the lift distribution span-wise to achieve a higher level of performance while maintaining good handling characteristics. So people have worked this area understand well that this is quite a challenge to balance stability and performance, and Alon points out that it is all too easy to create a design that performs poorly. I think my original configuration might fall into that category. It had okay performance, but as soon as you pushed it faster or tried to float a little slower, the performance dropped off rapidly. So my new design will attempt to avoid those problems. So let's go on and look at the baseline configuration for my new wing. That's right here. It is a 15-meter span. So instead of being 38-foot span, it's 49-foot span, so 11 feet more of wingspan than the original design. It's slightly smaller in wing area. This one's running, this particular design that I have up here is at 147.6 square feet. My original one was up around 160 square feet. This has higher wing loading, better high-speed flight, and I'm going to compensate for the higher wing loading by including flaps on the design that the pilot can lower for takeoffs and landings to achieve a lower end on the stall speed and get speeds down to where it's foot launchable and foot landable. Now here you see the same induced drag simulation behind the wing, and I'll let it cycle through its angles of attack here, and you'll see that this induced drag is significantly different than my original design. It is quite highly loaded in the center, but I want to note something about the winglets here. I want you to watch the induced drag here out by the winglets. You'll see that this area here is unlike other flying wing designs. If you were to put these winglets out at the wingtip, you would not get this result that we're going to see coming up here, and I'm going to try to pause it here at the right point so we can point it out there. There's a good spot. We see an increase here in induced drag right behind the winglet. And one has to stop and say, wait a second, where's that coming from? This is induced drag, and it is slightly outboard of the winglets, and there's a reason for that. This is not just the drag of the winglet itself flying through the air. This is the induced drag of the wing. And the only way that the induced drag of the wing can be increased like this locally is if the lift on the wing is increased locally. And what's actually happening here is the winglet is improving the flow over the wing and making the wing actually more efficient in this area. It gives the wing the ability to generate more lift for a given angle of attack. And that is because this winglet is affecting a large flow field around the wing. It's probably affecting the flow field twice its height and multiple times its width, and it is actually causing the flow to be straightened over the wing somewhat, and that's improving the performance of the wing. If this wingtip or if this winglet were not here, we're out at the wingtip, you would not see this here at all. It'd be gone. So one of the reasons for putting the winglets inboard is to get a little bump in performance on the wing. And the hope is that improved performance of the wing will help compensate for the added drag in the winglet, and thereby compensate in terms of the loss of performance by adding the winglets, the drag due to the winglets, excuse me. And we're going to see how that actually works out here in a few moments. But I wanted to point that out to you because it's one of the fascinating features of putting the winglets slightly inboard. Let's go back to our ISO view. Take a look at this. I should tell you some of the other basics about this design. I'm using an ACA 23015 here at the root. And on this particular configuration, it has a 23015 here at the wing joint, and then a 23012 out here at the tip. I'm using a 0008 symmetrical airfoil on the winglets. The reason I'm using these airfoils is because they have been around for decades and decades. They have proven performance. They have been studied endlessly in wind tunnels. When you look up numbers for these airfoils, you know for sure what you're getting. And this airfoil I used on my original wing flies very nice. This airfoils that were used on the Mitchell wing, which is hugely successful flying wing, brilliant design. And rather than trying to generate new airfoils for the aircraft, I decided to go with known entities and play with other parameters. The wing has about 2 degrees of dihedral in it, and the washout currently on this configuration is a linear washout from the root to the tip. It is we call the root 0, of course, and the tip is -8 degrees. So 8 degrees of washout at the tip, and it's linear along the path. This wing joint here is where the wing will come apart for transportation. There's actually a 2-foot wide center section here. So, and then there's a 7-foot long midsection. I'm just not showing the joint for the center section, which has the cockpit associated with it. And then there's a field joint that'll be out here at the winglet. The last 4 or 5 feet of the panel comes off also. So there's 1, 2, 3 panels on each side, and then 1 center section. So there's a total of 7 sections of this wing. Now I have the actual final configuration, the airfoil here at the first field joint is 23012. So it's a linear taper from a 23015 to a 23012, and then a constant airfoil out to the tip. And that gives a little better speed range performance. So let me go back and animate this, and we'll watch it go through the cycle. And I'm going to switch over to the spanwise lift distribution. Let me get back to graph 4 here and zoom in a little bit further and let you see the whole platform here. So what you're seeing here in this spanwise lift distribution is a little less bell-shaped for most of it. Sorry, some of it's going off the top of the screen. Let me see if I can shrink that down a bit. And you're seeing something that is rounded off in the middle and then kind of flat out to the tips, and that comes pretty close to what is called the parental lift distribution, which is intended to deliver higher performance from the wing. You get a better span efficiency factor out of it. It's what Al Bowers is using for his current flying wing project. And what you'll see here as it goes down to lower angle of attack, we'll wait for it to come back down and then I'll pause it. Just a couple more swipes here. Down she comes back down again. And I'm going to stop it here pretty soon. Right about there. Okay. So a couple other features that you're seeing here. We get back to more of the bell-shaped lift distribution here. You're seeing this lift reflex up and go out to 0. This means that this aircraft, when it's at slightly lower angles of attack, will have proverse yaw going into the turns. Al Bowers is doing the same thing, but he has much more profound effect. We're going to take a look at that in a moment. And then you see these 2 little funny bumps here. This is the spanwise lift distribution. So this is lift, is what you're looking at. And why is that bump there? Well, got to stop and think for a moment. Oh yeah, that's right. That's where the winglets are. The winglets are located here. And you can see that they're actually causing the wing to have a little bump up and lift. And you see that little bobble here.
and then you're going to see a little bobble in the lift distribution in this zone. This is where the field joint is, and the airfoil changes from there outboard, and then we have another little bobble out here where the winglets are. So if I were to run the design without the winglets, these go away. And that gives you a look at what the lift distribution is for the baseline Klingberg Wing Mark II. Let me stop that animation. And let's go quickly look at the one without the winglets. This is the same wing without the winglets. Let's go look at the graph. Let me get over to, let me go ahead and animate this. And I'm going to go over and look at graph 4. And I'm going to go over here to the lift distribution. Now I'll go to graph 4. Sorry about that. Let me shrink down. And I'm just running this one quickly so you can take a look at this and see there are no bumps here in lift from the added lift from the winglets, yet the spanwise lift distribution is pretty much the same. We see this tip effect here that is pretty much spot on with the parental lift distribution, and you'll notice that on the spanwise lift distribution here, you're not seeing any disruption of the curve here due to the winglet. So you can clearly see that the winglets are having an effect of the lift on the wing locally, and that increase in performance is due, in my mind, to straightening the flow on the wing and increasing its performance. I should note here that it is a well-known phenomena that when you have a swept wing, the flow will come in this direction towards the wing, and when it first hits the wing, it actually goes a little bit inboard and then begins to sweep outboard. And you'll see large spanwise flow conditions exist on some flying wings. I have some video up on my site, other video that you can go look at that has flow visualization, and you can actually go see that occur. So by placing the winglet here on the wing, approximately there, I am actually preventing some of that spanwise flow. It's acting as a very large wing fence and straightens the flow over the wing. Spanwise flow on flying wings is not a fun thing. It's one of the things that causes tip stalling and spinning. And spanwise flows are often aggravated by strip ailerons. They make it much worse. So my design is an attempt to avoid all of those problems. Now let's go back, let's stop this animation and go back and look at the original configuration, or the baseline configuration, I should say. Here we are back at the baseline, and let's just take a quick look at performance puller. Let's go over here over to L over D. And here's a CL over CD, same thing. Here we are, we're peaking out at 36.6. Once again, don't believe the absolute numbers, but we know that this number is much larger than my original configuration, 28 up to 36, a very significant improvement. But what I'm most interested in is that this portion of the curve is much flatter. Let's go quick look and remind ourselves what the original one looks like. There's my original flying wing. You see it really drops off quick on that side. And we go look at the new baseline, and we have a much better performing wing. We have a wider range of angles of attack where you have reasonable L over D. So we're looking at a drop here from about 36 down to 30 over an angle of attack that runs from about 5 degrees up to, well, way up there. So over, probably 10 degrees angle of attack, you only have a change of 5 in L over D, 5 out of 35 approximately. If we go back and look at my original wing, gosh, look at this. Here we are at, let's see, we got a drop off from here from about 28 down to 25. There's a drop of 3 in L over D, and that's over a range of about 4 degrees up to 10. So only 6 degrees angle of attack, and you've lost 3 L over D out of 28. So really, the new design has a broader range of flight speeds that'll deliver good performance. And this is a result of placing the mean aerodynamic chord at about 43% of the semi-span. If the mean aerodynamic chord is inboard of 43% of the semi-span, you'll have a noticeable drop in performance. This is also outlined in that paper by Alain Crew. He does a little bit of math there to show how you arrive at that parameter. So I've set up my wing to meet that criteria of having the mean aerodynamic chord at least 43% of the semi-span. And indeed, it works out. The codes show that it increases performance. So then the question becomes, do we have decent stability on this wing compared to my original wing, which had reasonable stability? And this program will help us analyze that also. So if you want to take a break, now's the time to do it. Hit pause, go off, refresh yourself, and come back, and we'll tear on into some of the stability analysis.
Okay, I thought I'd take a short break in the middle of the video here. I hope you're enjoying the content. I hope you're entertained, maybe learning something as we go along. And if you do appreciate all this work that I do to put into these videos and all the information that I present that's hard to find anywhere else, I ask you to please look below, see the thanks button, click on that thanks button, send me your thanks. All funds are greatly appreciated and go directly to supporting test flying the glider, which is a very expensive process. So any thanks you can give, greatly appreciated. And if you really want to support, I invite you to come on over to Patreon. My patrons are the best. They have supported this project for years and really made it all possible. And if you'd like inside information, commercial-free videos, all the other goodies, I got a great package for new members of all kinds of goodies that you'll find very useful. So if you have a mind to, go on over to Patreon.
What you see here is a lateral stability analysis of my original wing. This analysis shows both the amount of deflection as well as the rates. Here we see in degrees here, and here we see the rates. And as you can see, the peaks on both the amplitude and the rate are dropping off fairly rapidly here with each cycle, which means that this design is fairly well damped. And if excited in a lateral situation or perturbed, it will fairly quickly return to a steady state situation, which is exactly what we want for a nice stable flying wing. Keep in mind that this analysis is done over a very narrow range. It's done from 0 to 1 degree amplitude, and it's done in 10th degree increments on the analysis. There's various other analyses you can do with this program, but I find this one to be very useful in terms of determining whether the wing is actually nice to fly. That said, if you went into this program and did analysis on a design that you haven't flown, it might look good and fly lousy. It is a bit of a tricky area. So what I like to do is I actually build the models first. Take the models out, fly them, tweak the models until it's flying in a way that I find to be pleasant to handle or relatively benign. And then I go back and put those parameters into the program and take a look at it and see what the results are for that particular configuration. And then I use that data to do trade studies around that data, saying that it's either more or less stable. So first I establish a baseline with an actual flying aircraft model. Now, having done this for decades, I can fairly well judge the difference between the model and the full-size aircraft. They're not the same at all. You can't go out and build and fly a model and say, hey, the full-size aircraft is going to be exactly the same. It will not be. The scaling factors are very difficult to deal with. But having done both, I can come up with a fairly firm idea of if this model flies this way, the full-size aircraft will fly another particular way that's either better or worse, depending upon how the mass distributions are done. And I can go look at theoretical data such as this and say, if I made this change, it's going to make this change to the stability, and the end result on the aircraft will be thus and such. Actually, that's how Boeing does it. Boeing actually, as we were working on the 757 and 767 aircraft in the wind tunnel, before those aircraft were built, we would actually test the models in the wind tunnel, gather the data. We'd actually go out and make the same change on the full-size 747 aircraft, fly that around, collect data, run the 747 model in the wind tunnel, same configuration, and then compare all the data so that we could predict what the actual results would be with the full-size 757, 767 aircraft. It's a lot of work, it's very expensive, but it's really the only way that you get to a correct answer, or an answer that's closer to correct. So that said, the best way for me to do these, build model first, go out, fly it, see what I think of it, and then come back and do theoretical analysis on it. And that's basically what we've done here. Now, for a little bit of fun, we can go over and look at the actual wing itself. This control window allows me to adjust the initial amplitude of the disturbance. And here's the speed of the response. Let me put the amplitude back a little bit like that. And then we can activate this and watch it damp out. Now, what you're going to see here is greatly exaggerated. Remember, we're working over a range of only 1 degree. And you're going to see this thing oscillate all over the place. But in real life, you would not see this. The amplitudes are going to be very small in real life. It's exaggerated here for study purposes so I can compare the various cases. So let me restart this and hit animate, and there you see her go. There's 1 and 2 and 3 and 4, 5, 6, maybe one more, 7, 8. There's about 8 cycles, and it's pretty well damped out back to 0. Let's do that one more time. Let's click on it. You can watch it one more time. Now, you'll see that there is a little bit of rolling that's occurring as it's deflected in yaw, but it's not too bad, which is how the actual aircraft was. If you had a yaw disturbance, you'd get a little bit of roll, but pilot reactions are quick enough. They just tap the ailerons and take care of that roll as it occurred. Now, if you have a bad design, you can actually get a coupling between the equations of motion for yaw and roll, and that's called Dutch roll. And Dutch roll is usually at an amplitude and a frequency such that if the pilot tries to correct, he'll actually make it worse, and you get pilot-induced oscillations, which is PIO. So Dutch roll is a bad thing on flying wings. It's something that occurs quite easily because of the nature of the aircraft. As it starts to yaw around, the wing that comes forward starts to generate more lift. It starts to roll. This causes adverse yaw, causing a forcing moment back the other way, and it just gets swinging back and forth and rolling, and if you're ever flying one of those, it can be quite disconcerting. Not necessarily hazardous right away. If you let go of the stick, the aircraft will damp itself out, but not fun to fly. One of the ways of ensuring that the yaw and roll moment equations are not coupled is to adjust the dihedral of the wing. Now this wing has, and let me go over here and I'll show you the definition of this wing. I'll go into edit and into define, and you'll see right here, excuse me, let's get that guy back in the window. This design is the same as my full-size original flying wing. It actually has 1 degree negative dihedral, and what that actually meant is that the bottom of the spar, which is at the quarter chord point, so in other words, the quarter chord point of the wing is flat, horizontal. And if I change this, and let's just put in 3 degrees here for fun, because 3 degrees is not an odd number. It's pretty common amount of dihedral in a lot of different configurations, including flying wings. So I've now changed this design. It has 3 degrees of dihedral in it, and we have to go back and redo the all the analysis on it so that we can get all the numbers again, because we've changed the dihedral. The program has to go back and reanalyze that. So we'll zip through that here. That was pretty quick. Close that. So there's the new induced drag with this dihedral. It's not going to be much different than the original one. And then we go back over and redo the stability analysis. Go back over here to stability, 3D panel, viscous, yes, okay, we're all set there. And there we go there. And we hit yes there, and we set back up, and now we have to reanalyze for the stability characteristics with 3 degrees of dihedral instead of -1 or 1 degree of anhedral, if you prefer. That's the other way to say it. The program will chunk through this fairly quick. By the way, I'm doing these runs on a Lenovo laptop, pretty good processors, NVIDIA's in it. It's actually a gaming computer, and I find that the gaming laptops have the power that you need to run a program like this fairly efficiently, where you're not sitting here for 10 minutes waiting for it to chunk through all of these iterations. And there we go, we're done. And now I can grab this wing and move them back over here. And let's take a look at that stability again. Let's animate. And there she goes. Wow, look at that. So now you see the amplitudes are greater, and you get a little bit more rolling, and that's the beginning of the coupling of the equations of roll and yaw, which is not something you want. Let's watch that one more time. And there she goes. So that's why my original wing had 1 degree of anhedral, and decouple the equations of motion and make it a little nicer to fly and avoid that Dutch roll. If we go back over here and look at the stability graphs, you probably don't recall the other ones. I barely recall them myself, but this number here, this first rate peak on the other one was actually pretty close to 1. So we've had about a 30% increase in rate. And down here we've had an increase in amplitude also, increase of about 0.3 here also. So both amplitude and rates are increased by increasing the dihedral. So on flying wings, don't think that you're going to solve your problems by increasing the dihedral. You might actually make them worse if you couple up those equations of motion. It should be bad. Now, that said, you put on winglets, tire situation changes. With winglets on, the yaw damping goes up significantly, and you're much less likely to have coupling of those equations of motion. So let's go here and look at another configuration. Let's see, that is that one. Let's see, we go back over here. Let's go look up at a well-known design. This is the Horton 10. And to avoid confusion, this is not Al Bauer's design, not at all. What I'm about to show you is not the performance of his wing in any way, shape, or form. These are the best Horton 10 numbers I could come up with. This aircraft design has been modeled many times, and its performance is pretty well known. Without winglets, it's known to be fairly nice to fly. It doesn't have Dutch roll, as far as I know. Most of the models fly well, and it has decent yaw stability and damping, good pitch stability. And actually, most of them are flown with somewhere around 3 degrees of dihedral, and I think that's about what I have in this particular one. Current plane, let's go over here to edit, take a look at it, see what I got in it. 2 degrees of dihedral on this particular one, but I've seen them much steeper. So let's go look at some of the same things that we looked at for my original wing and the baseline for the Klingberg Wing Mark II. Let's chunk through the angles of attack. And you'll notice that because there's no winglets here, you're not seeing any increase in induced drag or equivalent lift increase because there are no winglets there. And you're seeing highly loaded in the center section, less loaded or actually negatively loaded at the tips. There's 10 degrees of washout in this wing. Let me turn on the airfoil names, remind myself. Just to do a fair comparison between my designs and the Horton design, I have no idea what the coordinates are for the Horton airfoils. I didn't use those. So I just plopped in the same NACA airfoils that I'm using. This has 10 degrees linear twist from the root to the tip, and it's a linear interpolation between the 23015 at the root and 23012 out at the tip. And let's go back and stop this animation. You see it go through that. And let's take a look at its lift distribution. Let's go over here to graph number 4. Take a look. Let me shrink this down so you can see the whole thing. There you see a very classic bell-shaped lift distribution. It's what the Horton brothers used on most of their flying wings. Worked out well for them. And they got good performance. So let's fire up the animation again here. We'll watch it chunk through. You see that it's very bell-shaped there at the maximum angle of attack, and as it comes down here, we'll pass through kind of a Parental distribution right about there, and then you're going to watch the tips come up, and they're going to come up quite steeply there. Out at the wingtip, they're negatively loaded. Now, that characteristic here, I'll stop the animation, we'll go down and we'll take a close look at that. Let's go down here to 4 degrees. You'll notice that the tips are negatively loaded here. That's the extra twist that's in the wing and the planform of the wing, so forth. This is what makes this wing reasonably nice to fly with standard elevons, is that as you roll into a turn, you actually get proverse yaw, and it helps. That proverse yaw helps decouple and prevent Dutch rolling. Decouples the equations of motion, prevents Dutch rolling. That's why you can have 2 degrees of dihedral in this wing and not have a lot of problems with Dutch rolling. It's because of the proverse yaw that's generated by this lift distribution. The question becomes, is this lift distribution or this configuration higher performance or lower performance than can be achieved with other configurations that actually use winglets to improve the stability and maybe flatten out the wing to prevent coupling of the equations of motion? There are a lot of parameters to play with. There's probably 20 key ones that you can pull the levers on. But I've narrowed it down over the years to some of the driving ones that I'm going to demonstrate for you here. We have to keep in mind, Alon Cruz said, got to have the mean aerodynamic chord at 43% of the semi-spad in order to achieve decent performance. And then we know that we want the tips downloaded to help prevent weird Dutch rolling situations, and that's without winglets. So flip a coin. What do you want? You want performance, you want stability. Or you can put winglets on it and pay a price on drag. Okay, so let's take a look at performance of the Horton wing and do a comparison to my new wing with and without winglets. Remember, absolute numbers are not valid, but comparative numbers are. So let's take a look here. I've set up these graphs to have the same scales so that it's easy to compare. Right here, if you look in, if I do this a little bit, there we go. If you watch up here, you can see the numbers of where my cursor is. But right here, right between here and here, we have maximum L over D on this Horton wing design. And it's showing it has an L over D about 37.5 in round numbers, and that's at about 8.3 degrees angle of attack. Actually, it runs from about 8 degrees all the way out to about 8.5 degrees. So right within this range, you have peak performance on this wing. I should have mentioned earlier that the Horton design also has about 3 degrees more sweep than my wing has, and that enhances its yaw stability. So here, let's take a look at the range of performance here. And just for grins, let's say how many degrees angle of attack before you lose, before you drop down to L over D of 35. And then we'll also look at what happens when you go down to an angle of attack of 4 degrees, which would be nose way down, pushing as fast as you can to get to the next thermal. We have a drop off from the peak of 37.4 or so. Let's see, 37.4 down to 35, and at 35 we're at about 6 degrees angle of attack. So that really is about 2 degrees angle of attack reduction. Put the nose down 2 degrees, and you've dropped the L over D by a value of 3, which is not huge. 10% decrease in L over D. Go a little faster. Now, if I extrapolate this curve out, the program analysis would not take it out to 12 degrees, but I can extrapolate here visually and say at the high angle of attack end, we'd be back down to 35 L over D out here at about 11 3/4 degree angle of attack. So you can slow this baby up and float it in a thermal or in light ridge lift quite reasonably. This drop off in performance is not bad. You got a wide range of angle of attack that you can fly it on. Overall, very good performance for a flying wing. So let's go take a look at my design without winglets, which is probably most comparable to the Horton design. Remember, my design has 3 degrees less sweep, has less taper, and it has less twist in the wing. What we have here is basically a very similar L/D curve. It's just shifted towards the high-speed end, the lower angle of attack end. In other words, the ability to fly fast between thermals will be superior on this configuration. We'll look at the overall performance, 37.4. Pretty much identical to the Horton design. This is without winglets. It drops down to 35 up here at about 12.2 degrees, which is less than the Horton design. In other words, this particular design will not slow up as well. It will slow up, but it will not maintain its performance at really high angles of attack like the Horton design will. That is simply because it has less twist in this wing. This is 8 degrees of twist. The Horton has 10 degrees of twist. The Horton will slow up better. And over here, we're dropping down to 35 at about 5.2 degrees or so. Let's quick flip back to the Horton to remind myself where that was. 35 was up here at about 6.2 degrees. So we can actually go to on my current configuration without winglets, you can go to lower angle of attack and maintain the same performance. So that means at a given speed, at higher speeds, my wing will have better L/D than the Horton design. So the Horton will slow up better and fly in thermals and light ridge lift better. My design will get you to the next thermal faster. You can have thermals spaced further apart and still get there. It's a trade-off. So I'm compensating for this difference by including flaps on my design. Now, of course, you could put flaps on the Horton, but most people don't. There's a reason for that. Because of the extra sweep of the wing and other factors, you put flaps, inboard flaps on the Horton design, you can have some pitch stability problems as you deploy the flaps. You get nose up and nose down. It can be a bit of a problem. There might be a way to finagle that. I haven't worked the Horton design to figure out if you can add flaps without affecting the pitching moment. My design, I did from scratch so that flaps could be added, and you can deflect the flaps at any angle from 0 to 90 degrees down and have no impact on the pitching moment curve. So you have no elevon deflection required when you deploy the flaps. So on my design, you can deploy flaps, increase your max CL, and maintain high performance in light lift conditions, and retract the flaps and go fast between thermals, which is, of course, exactly what they do in high-performance sailplanes in order to achieve the best performance over a wide range of flight conditions. However, my design, by having less twist, less taper, and less sweep, is less stable than the Horton design. So I have to go put winglets on it in order to get that stability back. And that's the big question. Can you add the winglets and not kill your performance completely? So here we are, we're sitting at about 37.5 on the L/D, and let's go take a quick look at the performance curve with winglets. Here we are with winglets. Let's take a look. And we are at 36.5, 36.6. So it has cost us almost a full point L/D, not quite, 8/10, 8.5. I don't have my little calculator going right now, but less performance. Round numbers, 1 L/D less for putting the winglets on there. So now the key question is, can I get that 1 L/D back by diddling with the twist in the wing? If I can adjust the twist or the airfoils, maintain stability, same stability as I have with the auto yaw winglets, but get that performance back that I was paying for by sticking the winglets on there. And that's what most of my recent studies have been about. Before we go any further, now would be a good time for you to take another break. Go charge up your beverage, add to the snacks, and come on back when you're done with that. And we'll move on to the next section. We're going to look a little bit more at comparison of stability between the Horton design and my current Klingberg Wing Mark II. Okay, so let's take a closer look at stability of the various configurations. What I'm showing here, just as a reminder, are the stability curves for my original wing. I've set up all of these graphs to have the same amplitudes on the y-axis so that they're fairly easy to compare. And of course we see here that both the rates and angles are damping out fairly quick on the original design, although it does go through a few cycles before that happens. We remind ourselves that we're looking at an analysis between 0 and 1 degrees of lateral displacement. So let's go look at the Horton design. My original wing was flyable. It annoyed some people, but I was okay with it. But maybe we can do better. So here's the Horton design. And scales are the same. And you'll see that both the amplitudes and rates are considerably lower than my original design. We're looking at an amplitude here on this first full cycle about, let's see, we're up around about 0.42. Click back real quick to my original design. We're looking at 0.6. So 50% more in terms of the amplitude. Now remember, that's degrees. Most people aren't going to be able to visually see a difference between 0.4 and 0.6 degrees, but that's just the engineering facts of the situation. We go back to the Horton. Let's look at the rate. The rates get up a little better than 0.6. And back to my original wing, take a look at the rate. Rate gets up to 1.5. So rates and amplitudes are considerably higher on my original wing, yet it was flyable. The Horton design with more twist, more sweep, is better damped in terms of lateral stability. So in that regard, a superior design. Let's go look at my design without winglets. Here it is right here. We're looking at rates a little higher than 0.6, pushing on up towards 0.7. So that's a higher rate than the Horton wing. And we're looking at an amplitude here of up around 0.45, so slightly higher amplitudes. What you're seeing is a greater distance between peaks, though, which means that this design has slightly higher amplitudes, a little bit higher on the rates, but it takes longer to damp out. And I bet you if you flew the Horton compared to mine without winglets, you would clearly see the difference even on the models, that my current design takes longer to damp out. And that's because I have less sweep, I have less twist, and I have a different taper ratio. So the span-wise lift distribution on my current wing is closer to elliptical than the Horton wing, and therefore it's less damped laterally, and it would oscillate around more before it damps out. So the question here is, we know that my wing without winglets will achieve performance that's superior to the Horton wing, but its stability is a little bit less. So can we gain that stability back with the winglets and not kill the performance? And remember, we're making up for the performance difference by having flaps so we can get down to lower speed. So right now, my design without winglets will give you better performance at the high speed end than the Horton design. A little less performance at the low end, unless you have flaps. Put the flaps on it, you'll get the same performance at the low end, but overall it has less lateral stability. And just for fun, let's go take a look at them actually move around and perform. That's always fun to watch. Let's go here to the Horton first, and let's animate it. We'll put it up that amplitude over there about 3/4 of max. We'll put the speed up to max, and we'll hit animate, and we'll watch it. We'll watch it go through the cycle, and there she goes. 2, 3, and 4, and 5. And 6 as it damps out here. And actually this will go somewhere around 10 or 12 cycles before it's fully damped out. You can see Horton 10 models flying on YouTube. Go look for them, and you'll see that they fly fairly nice. It's not like you see them yawing all over the sky and being a problem. So remember, these visual simulations here, the amplitudes and rates are greatly increased so that we can actually visually see them. So let's, now that we've seen that, let's go take a look at my original wing. Same type of situation. Let's go over here and take a look at it. We'll set up the stability to be the same. We're at 3/4 on amplitude, full on the speed. We'll restart, we'll hit animate, and there she goes. And what you see is you can quickly see the higher rates, and amplitudes are greater also, but it damps out a little bit quicker. This will damp out in about 8 cycles, 8-9 cycles. Horton takes 10, 12 cycles. Not that you'd notice a difference flying a model from the ground. You might notice in the air, you might not. So the amplitudes and rates are higher, damps out a little bit quicker. It's mostly due to the mass distribution on my original wing being closer to the center of the wing. Because of its high span, low taper ratio, the Horton inherently has the mass of the semi-span further outboard, and that becomes a forcing function, and it overcomes the damping that's available, so you go through more cycles before you damp out. It's the advantage of having a stubbier flying wing. You can keep the mass towards the center, and it will damp out quicker any lateral excursions that you have. Drawback is you don't have as much performance. So once again, a trade-off. Now let's go look at my current wing without winglets. Let's go take a look at that yaw around. We'll set it up the same way. We'll set amplitude the same. We can speed up there, and then you can watch this baby really go. And there she goes. And you'll see rates and amplitudes that are kind of similar to my original wing. Damps out kind of the same. Not as nice as the Horton, but still stable. And it does damp out fairly quick. So we've bought some higher performance here in terms of L over D, but we've taken a chunk out of the flyability or the nice handling. This wing without winglets would be about the same or maybe even worse than my original wing. So let's go look at the case of this wing with winglets. And here you can see on the curves that the rate is much, much lower. We're looking at a rate of only about 0.4 instead of around 0.6. So you got a 50% reduction in rate. And here we're looking at an amplitude around 0.2 instead of 0.4. So we got about a 50% reduction in amplitude and rate by adding the winglets. And let's go watch that happen. So there it is. Let's set it up the same. Speed up there. The amplitude up to about 3/4. Restart. We'll hit animate. And you can watch her go here. And you're going to see this damp out pretty quick. And boom. So this is a lot more like the Horton design. So we have higher range of good L over D performance, wider range of performance, higher speed end, much better L over D at high speed. We'll buy the low speed end by putting flaps on it. We put the winglets on it, and we get really nice stability. Now, if you go watch my video on auto yaw winglets and how they work, that explains about the drag situation with the auto yaw winglets, and I cannot simulate that here in this program. This program doesn't allow me to set up winglets that will free stream outboard, so I can't actually look at how quickly damped this design is with the auto yaw winglets. But I know from the model that it is heavily damped. The auto yaw winglets just damp it out and nothing flat. In practice on the model, I've seen any yaw excursions damped out in anywhere between a 1/4 second to 1/3 of a second. So the event's over before the pilot would ever realize it, and that's part of the magic of the auto yaw winglets. When we get down to the end of this video, I'm going to go to a clip of the model flying, and we can actually count through frames of video, and you'll see how quickly that system operates to damp out the wing. And when you fly the wing, you don't see any adverse yaw. You don't see any Dutch rolling, you would feel that you're flying a very conventional configuration. No bad behaviors at all.
This video clip shows one of my earlier configurations that had a double taper on the wing. I've since abandoned that configuration because it still had some stall spin characteristic problems. But this video shows the Elevon and auto yaw winglet working as per normal. So it's a good little clip to demonstrate how the system functions. You're going to see this twice. You're going to see it once in real time and once in slow motion. You'll see the Elevon go down, winglet open, Elevon come up, and winglet close. So here we go in real time. Boy, that sure was fast, wasn't it? That took about 1 second total for the entire event to occur, much faster than the pilot would ever notice anything happening. So I'm going to show it to you here now at 1/10 normal speed and talk you through the event. And we're just about ready to go here. On your mark, get set, and go. So the Elevon goes down, the wing begins to roll, little adverse yaw, the winglet is opening, the winglet's open, Elevon comes back up, and the winglet closes, and the plane stays in perfect coordination throughout the turn.
So we have the stability situation taken care of. This will be a nice handling aircraft. We have the performance mostly taken care of. We have similar performance, better at the high speed end, not quite as good at the low speed end. Got to put some flaps on it at the low speed end. But now let's go take a look at other parameter that we can tweak and see if we can actually jack the performance up a little bit higher, and still maintain reasonable stability, something that'd be nice to handle, yet exceed the performance of that Horton 10. So time for another break. Go off, do whatever you need to do, rub your eyes, clear your head, because I know it's a lot of heavy-duty technical information. The engineers out there are probably eating it up. Those that don't care less about engineering are long gone, and in between, people are just a little confused. So you might have to watch the video 4 or 5 times, but take a break now, clear your head, come on back, and we'll delve into how we're going to jack up the performance, yet maintain the nice handling. Welcome back, and here we are to the final segment of the video. We get down to that magic conclusion of what's the optimum configuration, which has taken me years to find, and you've only had to sit through maybe an hour's worth of me yakking away. But we're almost there. We're going to get down to that final golden number, and you're going to see what it does for us. We're going to go through 3 more configurations. All of the 3 configurations are identical with one exception, and that is a change in the washout pattern. We're going to adjust the washout patterns to slowly walk away from the bell-shaped lift distribution more to an elliptical lift distribution. We're still maintaining a mean aerodynamic chord at 43% of the semi-span, but we're going to change the twist in the wing to change the lift distribution and hopefully make the wing a little more efficient. So if you recall, the original wing has 8 degrees of linear washout from the root all the way out to the tip, and that meant that at this field joint the washout was about 2.3 degrees. So for this particular configuration, twist option 2, I have changed the washout pattern such that there is no washout in this center section. This is flat, not twisted at all, and there's 8 degrees of washout from the field joint out to the tip. So all of the washout that is contributing to pitch and yaw stability occurs in this outer portion of the wing. That should make the idea behind that, the idea behind this change. Boy, that's being very persnickety. There it goes, gone. So the idea behind changing to 0 washout in the center section is that this center section of the wing will operate more efficiently. Okay, so by making the outboard or the outer panel of the wing do the heavy lifting, pun intended, of dealing with the pitch and yaw stability, we'll make the inboard portion of the wing more efficient and maybe not have to twist the wing quite as much in total to achieve the stability that we want, especially with the auto yaw winglets doing their thing and keeping us damped down really low on the rates and amplitudes. So this configuration, no washout out to this joint, 8 degrees linear out to here, and let's take a look at the performance curve on this. Let's go over, take a look. Let's go over on graph 4 here, look at the L over D, and let's see if I can't get this somewhat similar plot here. I should have had this preset for you, but I'll just do it real quick here. Scales. We want to go up to about 15 degrees here. Turn that off. Get that up about 15. And turn that off. Run this one up to about somewhere up around 40. Okay. So here we are. We're showing a max L over D on this design of 37.25. And that is with the changed washout, and the winglets are on there. So let's go back quickly and look at the baseline configuration with the linear washout and winglets. We'll go to the polar, and what do we have here? We had 36.68, and we go back over here to the option 2, and we got 37.2. So we gained 4/10, half. We got a half a point of L over D improvement, and we're probably not going to have any significant negative impact on the yaw stability, because the yaw stability is being dominated by the auto yaw winglets. So a little bit more performance and probably no change in stability. So let's go look at another situation. Let's just say we're a little worried about pitch stability, yaw stability, because there's less of the wing that's actually twisted. It's still twisted 8 degrees, but the total area of the wing that's twisted is less. So let's just say that we're a little bit worried about that, and let's go look at a configuration that's a little bit different than that. This configuration is highly similar to the last one. There is 0 washout in the inboard portion, but now there's 10 degrees of washout in the outboard portion. By twisting this more, we'll get more pitch stability and we'll get more yaw stability, but we'll pay a penalty on performance, most likely. I should have noted earlier that between the baseline configuration and these variations, I've also changed the airfoil. That's to maintain high speed performance. On the baseline, this is a 23015 here at this field joint, and on these 3 variations, it's a 23012. That helps jack up the high speed performance a little bit better. Let's go look at the polar on this. Here's graph 4, see what we got. I'm not going to fiddle with the graph here, but here we go. Our maximum L over D here. Oh, we paid a penalty. We're up here around 35.8. So 35.8 with a 10 degrees of twist, better stability, less performance. Go here to the 8 degrees of twist just in the outer panel, and it's 37.4, and back to the original is 36.68. So what this tells us overall is that maintaining relatively low twist, stay under 10 degrees, and move that twist as far outboard as possible will actually gain us L over D and maintain stability. So how do you do that? Well, you just twist the bejesus out of the end of the wing. And that's essentially what the Horton brothers did. The Horton brothers used a non-linear twist in their wing. And I think they discovered along the way it became problematic to build. If you have a wing that has all of a sudden the last 3 feet of the wing is twisting 6 or 7 degrees of twist in a few feet of wing, that can be difficult to build. And then it becomes a question at high speed flight, what does that do to the performance of the wing? Probably cuts into it. So there's somewhere in there, there's a compromise. What's a reasonable amount of twist to put over a given span of the wing? And that's the third configuration. I've worked a bunch of variations on it. I'm just going to take you down to the bottom line, which I know you've been waiting to hear. That'd be this configuration. So what I've done here is, because I have an additional field joint that I'm going to have here for disassembling the wing, I've created a staggered washout here. There's 0 degrees of washout in the center panel. There is 3 degrees of washout from the first field joint to the second field joint. So only 3 degrees over 11 feet of wing. And then the last 5 feet of wing goes from 3 degrees to 8 degrees. So we have 5 degrees of twist in the last 5 feet of wing. And I felt a degree of twist per foot of wing is something that's buildable. And not look too odd, and probably not too draggy at the high speed end. So let's go take a look at the puller of this wing. We go over here and look at graph 4. And what do we got? We got us a maximum L over D of almost 38. And that's with the winglets. So here we've added winglets, which cut into our performance, but it changed the twist of the wing, making the center of the wing not twisted, the mid portion of the wing moderately twisted, and then the last little tip fairly heavily twisted, making the tips very efficient at being essentially the tail of the aircraft. If this were a conventional configuration, you would call those tips the tail. And conventional configurations are very efficient because the tail is way behind the main wing. And because we have a swept wing here, what is now essentially the tail of the aircraft, the wingtip, is not all that far behind the portion of the wing that's doing all the flying and lifting. But this is a good compromise. So we've bumped the performance from about 36.5 up to almost 38. We've gained 1.5 in L over D by changing the twist of the wing. The winglets are on there, so we've overcome the performance hit that we took with the winglets. And let's go back and remind ourselves where we were with the Horton. Let's go out to the Horton and look at its puller one more time. Let's go over here to the puller. And here's the Horton sitting at, what was it? 37.5. So we're beating the Horton by a whole half a point of L over D. Now, would you ever actually see that in real life? Maybe, maybe not. However, my wing with the winglets is a lot more damped in yaw. There's less likelihood of Dutch rolling. It'll be more pleasant to fly. The auto yaw winglets and where they're placed on the wing prevents spins. The model is entirely spin proof. And by including flaps in the design, we'll be able to maintain high performance over a wide speed range. So this is the point that I'm at currently with the design. It's a compromise all the way around. I would not sit here and say it's going to have the same performance as a conventional configuration, but then, hey, that conventional configuration is not going to look as cool in flight as my final design. So there we go. There's the final puller. It's not plotted on the same axes as the other ones, but I assure you that overall this is going to be higher performance. So to finish up here, let's take a look at the span-wise lift distribution between the Horton design and my final optimized configuration. So what we're looking at here is the span-wise lift distribution at 7 degrees angle of attack. And we're showing the center of the wings pulling, you might get the numbers up here. Yep, can't see them. I guess it's not going to display them. We lost that guy there. Let's bring him back down. We're up here around, I guess, about 7.5 at the center of the wing. 0 out at the tips, of course. And a very classic bell-shaped lift distribution. And you're seeing that at this angle of attack, the tips are beginning to download to provide the pitching moment coefficient for stability. And let's take a quick look at a higher angle of attack. Let's suppose you get that nose cranked way up to slow up in a thermal or scratching along in light lift. And here we see we're pulling about 1.05 here at the center. And the difference here is the tips are now becoming positively loaded. You'll notice that in both configurations, this portion of the curve is relatively linear, and that's typical of a Parental lift distribution. Go back, look at the lower angle of attack again. Let's go back down to 7 degrees. Quite linear here. Now let's go look at my design, the same situation. Let's look at 7 degrees down here. I think we were down at 7. Let's look at 7. So you'll see that here in the middle we're pulling about 0.85, something like that. And you'll notice that this area is broader than the Horton design. That's because there is no twist in the inboard portion of the wing. Let me go back to the Horton. You'll see that it begins to round over on the Horton here right away. So that's the linear twist that's in the wing, minor amount of twist near the center of the wing. Go back to my design. And you'll also notice that the lift distribution is curved here along this portion of the curve. That is pushing more towards an elliptical lift distribution, which is what's buying the higher performance. The Parental lift distribution, that it would be very straight here. And then the tips here are in a lifting mode until you get out to the very end. As you get the last panel, the outboard panel of the wing is much more a Parental lift distribution. So we're buying performance on the inboard portion of the wing, and we're maintaining about the same performance on the outboard portion of the wing. And if I switch back over to the Horton and change angle of attack, let's change the angle of attack here up to 11 degrees here. Take a look at that. So at 11 degrees, you'll see the same kind of thing, that the center section is more efficient. This portion of the wing, the midspan, is being made to work harder. And out here, the tips are still performing well. So just to remind you, we'll go back to the Horton and look at the same situation. Let's go look at 11 degrees on the Horton, and you'll see that the tips are lifting heavily until you get down to the very end, but this portion of the lift curve is very linear here, so it's not quite as close. It's not as close to the elliptical lift distribution as one might want. Now, a pure elliptical lift distribution on a flying wing is not going to work well. You're either going to have gigantic winglets in order to provide the yaw stability or do something else. So all of these curves, they look similar, but those subtle differences between them make a difference of 1.5 points in L over D. So there you go. Bottom line, nonlinear twist in the wing, and use auto yaw winglets to take care of the need for yaw damping, yaw stability. And not only that, you gain the added advantage of preventing spanwise flow and stopping those nasty stall spins that occur when you're scratching around in a really light thermal. So, long story, it's only taken an hour or so of your time here, maybe a couple hours. Took me, believe it or not, to sort all of this out and truly understand it and solve that stall spin problem and the spanwise flow and apply the auto yaw winglets correctly and set up the controls. It's probably taken me 10 years of on and off work, mostly a lot of scratching my head trying to truly understand what's going on a flying wing and make it fly much more like a conventional aircraft in terms of safety, yet and achieve performance that's closer to conventional aircraft. I don't think flying wings will ever achieve the blow-away performance that you get from a conventional configuration, but when it comes down to a foot-launch aircraft, the flying wing has distinct advantages when it comes down to transportation and ground handling. Much easier to launch a flying wing when you're not dragging a tail on the ground trying to get off of some rocky slope or a cliff somewhere. So for the genre of foot-launched and foot-landed, flying wings have a distinct advantage. That's why most hang gliders are flying wings. And if you want true all-out performance, you go buy yourself a nice German composite sailplane, and you get your upper-end performance that way. So I hope you found this informative. Pass it around to your friends. Watch it again. If you're totally confused and have no idea what's going on, Don't write me. I've explained it as best I can. If you got a quickie, one little I don't get it, I say, hey, put it up on YouTube. I'll take a look at it. If I think I can answer it, great. If not, I'll let others take a swipe at it. But it's been fun. This is probably the most complex, least understood area of this type of aircraft design. So if you made it this far, you're a brave soul. Thanks for coming. Keep up, subscribe, tell your friends, watch all of the other videos, and follow with as I turn all of this theory into a real aircraft.
And there we go. We're at the end. I hope you really enjoyed all of that information. And last but not least, if you can give some thanks, that'd be great. Click the button down below or go over to the description of the video and click on the Patreon link and come on over and be a patron and join an august group of supporters. And in the meantime, I bid you fly safe and bye for now.